4. Plate tectonics. Plate tectonics, a crucial geological process, played a significant role in shaping the Earth's surface. The movements of tectonic plates led to the creation of continents through the collision and convergence of land masses and the formation of ocean basins through seafloor spreading. The formation of continents and oceans significantly affected Earth's climate, geology, and the evolution of life. And there's a reference down the bottom there, linked to that source: geology science, geology branches, historical geology, evolution of life. To have a look at. Continent provides a variety of environments for different ecosystems to thrive, while oceans played a role in regulating Earth's climate and supporting marine life or sea life. This dynamic interplay between the Earth's geology, its changing atmosphere, and the emergence of life continues to be a fascinating subject of study in Earth sciences. Life's emergence, prebiotic chemistry, early life forms, and the role of geology 1 billion years ago. Okay. Sunignites, prokaryotes, is that Latin or Greek? Probably Latin, right? Not too sure now. Cells without nuclear. Was it nuclei? Yeah, looks like it. Photosynthesis, etc., all the stages that it went through. It's evolution, right? The cycles. Okay, and then here's man. Dipithecus ramidus, Homo sapiens, and then they begin writing at that point somewhere. Prebiotic chemistry. The emergence of life on Earth is a complex and intriguing process that likely began with prebiotic chemistry, the chemistry that occurred before life as we know it existed, and so forth. Abiotic synthesis, Miller-Urey experiment. The famous Miller-Urey experiment conducted in the 1950s demonstrated that the conditions thought to exist on the early Earth, including a reducing atmosphere and lightning, could produce amino acids, suggesting that the prebiotic synthesis of organic compounds was possible. 3. Hydrothermal vents. Hydrothermal vent systems on the ocean floor are believed to be sites where prebiotic chemistry could have taken place. These environments provide the necessary heat, minerals, and chemical gradients for the formation of organic molecules. Early life forms. The transition from prebiotic chemistry to early life forms is one of the most challenging questions in the study of the origin of life. While there is no definitive evidence of how life began, several hypotheses, or guesswork, theories, right, and models have been proposed. 1. RNA world hypothesis. This hypothesis suggests that early life forms were based on ribonucleic acid, RNA, rather than deoxyribonucleic acid, DNA. RNA can both store genetic information and catalyze chemical reactions, making it a plausible candidate for the first self-replicating molecule. 2. Iron sulfur world hypothesis. Some researchers propose that life may have originated at hydrothermal vents, where iron and nickel sulfide minerals could have acted as catalysts for the synthesis of organic molecules. 3. Clay hypothesis. Minerals, particularly clay minerals, may have played a role in concentrating and organizing organic molecules, possibly facilitating the emergence of early life. The role of geology in the emergence of life. Geology played a crucial role in the emergence of life on Earth through several key processes: mineral catalysts, hydrothermal systems, subsurface habitats, plate tectonics. While the exact sequence of events leading to life's emergence remains a topic of scientific inquiry and debate, the interplay between prebiotic chemistry, early life forms, and geological processes underscores the interconnected nature of Earth's geology and the origins of life. You're not going to be talking about God here, right, in the debates, okay? This is all a scientific debate, right? Very unlikely that somebody in their circle, unless they're religious, a Christian or whatever, will say, yeah, but then God created it. Okay, there will be no. Science says, science shows, science proves, etc., etc. Plate tectonics and geological evolution, and it goes on about plate tectonics. So the Earth was probably one massive landmass. Okay, and the tectonic plates shifted, rubbed against each other, etc., etc., pushed one on top of the other, and maybe caused volcanic activity, lava to flow, separation, the land separated, and these waters were in between. Okay? As this African American guy states in one of his videos that we had a look at, according to, and he was like talking about the Israeli tourism board, and what it was actually saying, but they were hiding something along those lines. Yeah, it's really, really interesting. And he's talking about the tectonic plates shifting and volcanic activity. In Africa everything used to be in Africa, right? Where Israel is located today, that was all part of Africa before the tectonic plates shifted, etc., etc. And this Suez Canal, all those sort of rivers, were the dividers between Africa and where Israel is located today. Yeah, plate tectonics is a fundamental concept in geology that explains the movement of Earth's lithosphere. All these people talk about, the scientists talk about spheres. Okay? The lithosphere, the atmosphere, what's the other one? Etc., etc. So they're basically saying it's a sphere, okay? An orb or a globe. But other people out there will say, no, it's all flat. You don't know what you're talking about. Here's the proof. Well, that's over to you, right? Okay. Biblically, it says globe, the orb, and here it's saying from this geological science or geology science point of view, it's a sphere. Everything's spherical. Divergent boundaries. At divergent boundaries, tectonic plates move away from each other. This movement leads to the upwelling of molten rock from the mantle, creating mid-ocean ridges. As new crust forms and spreads, it gradually pushes old crust aside. Divergent boundaries are responsible for the creation of ocean basins and contribute to the overall growth of Earth's crust. 2. Convergent boundaries, transform boundaries, hotspots, subduction zones. Typically found at convergent boundaries are regions where one tectonic plate is forced beneath another, and so forth. The effects of plate tectonics on geological evolution are profound. They influence the formation and destruction of continents, the creation of mountain ranges, the distribution of earthquakes and volcanic activity, and the recycling of Earth's crust over geological timescales. The ongoing movement of tectonic plates is a dynamic and continuous process, shaping the Earth's surface and impacting the evolution, the cycles of its landscapes, the cycles, the development, etc., and ecosystems. It is a testament to the ever-changing nature of our planet and a driving force behind the geological diversity we observe today. Climate and environmental changes, geological evidence, mass extinctions, and the impact of continental drift. And there's all information here. Sedimentary rock layers, glacial deposits, fossil record, tree rings, and ice cores. Many extinctions and their causes. 1 Permian Triassic extinction, the Great Dying, occurring approximately 252 million years ago, another estimate ago. This is the most severe mass extinction in Earth's history. The causes may have included massive volcanic eruptions known as the Siberian traps, which released large amounts of volcanic gases and led to climate change. 2. Cretaceous Paleogene extinction, occurring around 66 million years ago. This event wiped out the dinosaurs. Okay, so that's the one that killed off the dinosaurs. The leading theory is that a massive asteroid impact in the Yucatan Peninsula, isn't it like, is that Yucatan, where's that? Is that South America? Okay. Anyway, in the Yucatan Peninsula, along with volcanic activity, caused widespread fires, darkness, and a nuclear winter effect, drastically altering the climate and ecosystems. End Permian extinction. About 252 million years ago, this event was associated with extensive volcanic eruptions in the Siberian traps. The release of volcanic gases, including carbon dioxide, led to abrupt global warming and ocean acidification, severely impacting marine life. Basically killed them off, right? Probably killed them off. 4. End Cretaceous extinction. The impact of a large asteroid, along with volcanic activity, led to rapid environmental changes. Acid rain, wildfires, and darkness caused by the impact triggered global cooling and disrupted food chains, affecting numerous species. Yeah, you cut off their food supply, or they'll die off, won't they? Well, unless they turn on each other and eat each other up, but then they'll probably die as well because there's no more food. Lack of food. Massive lack. Impact of continental drift on climate. The movement of continents driven by plate tectonics has had a significant impact on Earth's climate over geological timescales. Paleoclimatic shifts, ocean currents, biogeography, carbon cycle. Continental drift and its associated effects on climate have played a crucial role in shaping Earth's geological and environmental history. They have influenced the evolution of life, with that cycle, right? The distribution of ecosystems and the overall trajectory of the planet's climate over millions of years. In conclusion, the story of Earth's formation is a captivating journey through billions of years of cosmic evolution, or cycles. Key points in Earth's formation include the initial birth of our planet within the solar nebula, the differentiation into layers and dynamic interplay of geological processes that have shaped the Earth we know today. As we delve into Earth's formation, we are met with the realization that this ancient tale continues to be a subject of ongoing scientific research and discovery. New findings constantly deepen our understanding of the intricate processes and events that have crafted our planet. From the exploration of Earth's chemical composition to the investigation of its geological history, the quest to comprehend our world's origins remains an ever-evolving endeavour. The significance of understanding Earth's formation extends far beyond scientific curiosity. It holds profound implications for our planet's future. By unravelling the mysteries of how Earth came into being, we gain insights into the fundamental processes that govern our world. We learn about the geological forces that continue to shape our landscape. So there's some forces behind that, right? That continue to shape our landscapes, the mechanisms that regulate our climate, and the origins of life itself. So there's something behind all of that, be it a natural force, geological forces, or something supernatural, i.e. a deity or God. Furthermore, a comprehensive understanding of Earth's formation equips us with valuable knowledge that can inform our stewardship of the planet. It underscores the interconnectedness of all living and non-living elements on Earth, emphasizing the delicate balance we must maintain to ensure the sustainability of our ecosystems and the well-being of our species, i.e. the human race. Man, woman, children, right? And animals, right? Birds, etc. Our environment. In a world where climate change, resource depletion, and environmental challenges are pressing concerns, the lessons learned from Earth's formation serve as a guidepost for responsible and informed decision making. By appreciating the profound significance of our planet's origin story, we are better equipped to shape a future that preserves the beauty, diversity, and vitality of Earth for generations to come. And there's some more subjects here. The Hober meteorite, the Willamette meteorite, origin of water on Earth, we already covered that one. Geological evolution of continents, Earth's early atmosphere, we looked at that one. And then banded formations, iron formations in those rocks, archaeological studies, all that sort of stuff. Okay, so that's that one. And here's a table of contents. There's the information on that in comparison to the Brita or Genesis account. Okay, hypotheses about the origins of life. Key points. The Earth formed roughly 4.5 billion years ago, and life probably began between 3.5 and 3.9 billion years ago. This estimation differs, right? The operant Haldane hypothesis suggests that life arose gradually from inorganic molecules with building blocks like amino acids forming first and then combining to make complex polymers. The Miller-Urey experiment provided the first evidence that organic molecules needed for life could be formed from inorganic components. Some scientists support the RNA world hypothesis, which suggests that the first life was self-replicating RNA. Others favour the metabolism first hypothesis, placing metabolic networks before DNA or RNA. Simple organic compounds might have come to early Earth on meteorites. Here's introduction. If there were other life out there in the universe, how similar do you think it would be to life on Earth? Would it use DNA as its genetic material, like you and me? Would it even be made up of cells? We can only speculate about these questions, since we haven't yet found any life forms that hail from off of Earth. There's reports of aliens visiting and abducting people and sort of stuff. Okay? And people saying that they've, look at this video, they got hold of an alien and they cut him up and all this sort of stuff. Here it says that you can only speculate about these questions since we haven't found yet any life forms that hail from off of Earth. But we can think in a more informed way about whether life might exist on other planets and under what conditions by considering how life may have arisen right here on our own planet. In this article, it examines the scientific ideas about the origin of life on Earth, the when of life's origin, 3.5 billion years ago or more. It's an estimate. It's not a fixed or defined as fact, established fact date, right? It's well supported by fossils and radiometric dating, but the how is much less understood. In comparison to the central dogma or the theory of evolution, hypotheses about life's origins are much more hypothetical. No one is sure which hypothesis is correct, or if the correct hypothesis is still out there, waiting to be discovered. When did life appear on Earth? Geologists estimate that the Earth formed around 4.5 billion years ago. This estimate it's a guess, arrived at a possible date, comes from measuring, or era, time, period, right? Or age, comes from measuring the ages of the oldest rocks on Earth, as well as the ages of moon rocks and meteorites by radiometric dating, in which decay of radioactive isotopes is used to calculate the time since a rock's formation. For many millions of years, early Earth was pummeled by asteroids and other celestial objects, planets, etc. Not talking about heavenly beings or anything like that. Temperature also would have been very high with taking the form of gas, with water taking the form of gas, not a liquid. The first life might have emerged during a break in the asteroid bombardment between 4.4 and 4.0 billion years ago, when it was cool enough for water to condense into oceans. However, a second bombardment happened about 3.9 billion years ago. It's likely after this final go round that Earth became capable of supporting sustained life. The earliest fossil evidence of life. The earliest evidence of life on Earth comes from fossils discovered in Western Australia that date back to about 3.5 billion years ago. These fossils are of structures known as stromatolites, which are in many cases formed by the growth of layer upon layer of single-celled microbes, such as cyanobacteria. Was it cyano? No, it looks like cyanobacteria. Stromatolites are also made by present-day microbes, not just prehistoric ones. The earliest fossils of microbes themselves, rather than just their byproducts, preserve the remains of what scientists think are sulfur metabolizing bacteria. The fossils also come from Australia and date to about 3.4 billion years ago. Bacteria are relatively complex, suggesting that life probably began a good deal earlier than 3.5 billion years ago. However, the lack of earlier fossil evidence makes pinpointing the time of life's origin difficult, if not impossible. How might life have arisen? In the 1920s, Russian scientist Alexander Oparin and English scientist J.B.S. Haldane both separately proposed what's now called the Oparin-Haldane hypothesis, that life on Earth could have arisen step by step from non-living matter through a process of gradual chemical evolution, or cycles. Oparin and Haldane thought that the early Earth had a reducing atmosphere, meaning an oxygen-poor atmosphere in which molecules tend to donate electrons. Under these conditions, they suggested that simple organic molecules could have reacted with energy from lightning or the sun to form building blocks like amino acids, and nucleotides, which could have accumulated in the oceans, making a primordial soup. The building blocks could have combined in further reactions, forming large, more complex molecules, polymers like proteins and nucleic acids. perhaps, and pulls at the water's edge. The polymers could have assembled into units or structures that were capable of sustaining and replicating themselves. Oparin thought these might have been colonies of proteins clustered together to carry out metabolism, while Haldane suggested that macromolecules became enclosed in membranes to make cell-like structures. The details of this model are probably not quite correct. For instance, geologists now think the early atmosphere was not reducing, and it's unclear whether pools at the edge of the ocean are a likely site for life's first appearance. But the basic idea, a stepwise spontaneous formulation of simple, then more complex, then self-sustaining biological molecules or assemblies, is still at the core of most origins of life hypotheses today. Okay, then you have this RNA origin of life video, which features on YouTube, so we're not too sure if we play it here we might get some sort of copyright claim or strike or something like that on our channel. But basically it says here, RNA may have been the origin of life on Earth. Go on a whirlwind tour of RNA's evolving role through billions of years of evolutionary history. You can play the virtual RNA game at Nova Labs, created by Nova. Okay, and there's an article to follow. So we're going to jump back to YouTube and we're going to watch this